Okay, let us get started. We welcome you to this lecture 3 of our course on reinforcement learning. Today, we're going to elaborate on the theme of approximation value space, the workhorse of reinforcement learning. And we're going to try to interpret it in terms of Newton's method using visualization and the linear quadratic problem that we discussed in the previous lecture. Then the second half of the lecture, we're going to talk about how we formulate dynamic programming problems in a way that they are suitable for reinforcement learning approximations. We're going to discuss reformulations of such problems, give examples, and this is a theme that we're going to continue on in the next lecture. The fourth lecture is going to be primarily on examples, problem formulations, and the like. So here's the outline. There's a certain mapping in approximation value space, which I call critical. It's very important, and it relates cost approximation to policy performance. And we're going to discuss some general issues about that. And then we're going to review the material on infinite horizon linear quadratic problems, but focus on visualizations. And we're going to interpret approximation value space and relate it to Newton's method using this visualization. All of this is going to be for one-step look-ahead approximation value space. Then we're going to discuss multi-step look-ahead and how it can be viewed in terms of Newton's method. Then we're going to talk about stability issues, the region of stability, how it relates to approximation value space, Newton's method, rollout, policy iteration, and the like. And then we're going to discuss the formulation of practical problems as dynamic programming problems with examples. Reformulation techniques will include state augmentation and others. And finally, we're going to talk about multi-agent problems. And the homework that you have for next week is going to involve such a multi-agent problem. So let's start with this critical mapping. Let's consider online approximation in value space with one-step look ahead involving a system equation F, a cost per stage G, X is a state, U is the control, W is the stochastic disturbance, and we're going to consider an alpha discounted problem. What I'm going to discuss also can be generalized to undiscounted problems, but we'll focus on alpha discounted problem as part of our discussion. And here what we do is at any state that we encounter online, a state X, we consider all possible controls. Add the first step cost with future costs starting from the next state as evaluated by some cost approximation function, J tilde. Take the expected value of that over W and minimize overall controls. And that gives us the control that we are going to apply at state X. This is approximation value space with one step look ahead. And the approximation is here in this J tilde. In particular, we replace the optimal cost J star with an approximation in Bellman's equation. And instead of obtaining the optimal control, we obtain a suboptimal control because of this approximation. That suboptimal control is encoded in a one-step look-ahead policy, mu tilde, a lookup table that tells us at each state X what control to apply, mu tildes of X. So this is our standard framework, and there's a mapping that we want to focus on here. If J tilde where J star were optimal, then we obtain an optimal policy. Now, what happens when we degrade the approximation and from J star, we go on to J tilde. So we have an approximation error, J tilde minus J star. How does this approximation error affect the quality of this one-step look-ahead policy? So we want to find a relation between cost approximation and cost function of the one-step look-ahead policy and the corresponding approximation errors and performance errors? It's a critical question. It tells you when approximate right and left, how does this affect the result that you get? That's the question. So we want to ask questions around this issue. First of all, what's the relationship between J mu tilde and J tilde? Then this is one step look ahead. What if we were to use multi-step look ahead? What would change with this relationship? And finally, a quantitative measure of the effect of the size of look ahead. How many steps? We know that in practice, the more you increase the length of the look ahead, the better performance you're going to get. But what is the exact relationship between length of look ahead and improvement in performance? So that's the mapping we want to discuss. And there is a long-standing investigation on this issue, going back 50 years, maybe even more, which relates the approximation error and the performance error. And it says that these are related linearly. The more the approximation error is, the more deterioration there is the policy, and the relationship is linear. And this line here has slope. That's the estimate of the deterioration. The ratio between these two is less than 2 alpha to the L. L is the length of look ahead, divided by 1 minus alpha. Remember, this is a discounted problem, so alpha is less than 1. So as the look ahead size L increases, this bound becomes lower, becomes more favorable. Okay. Now, it's a classical bound. In my book, Pluton's Cyclis, 1996 book, we had several of those bounds. Some of them were quite intricate. Some of them were quite proud about them. But I'm going to argue that all of this is bad. It's an example of bad theory. We, of course, know we know from experience, well established, that these bounds are conservative. The real relationship between these two is much lower, okay? But it broadly has been thought that the linear relation is qualitatively correct. So even if this relation between the two is lower than the bound, it's still kind of linear. Now, the reality is far different. And these bounds are not only unrealistic, but they are misleading. If you use them for practice or theory, you're going to get along the wrong paths. They misdirect theoretical research and confuse the practitioners. Qualitatively, the relation between these two is not linear, but rather it is superlinear. That's what I'm showing here. Approximation error, performance error. Instead of the linear relation that the linear error bound postulates, the true relation is superlinear. In other words, it has this curved kind of shape. And if the approximation error is small, then the performance error is tiny. You're almost optimal. On the other hand, if the approximation error is significant, like you don't have a good neural network, it doesn't give you good approximations, then the approximation value space scheme can fail catastrophically. And this has been established with a lot of recent testing and research, the reference for which you can find in your book. And the key fact here is that these two are related through a superlinear relation that flows from Newton's method. This critical mapping that takes this into that is a Newton step for solving the Bellman equation. And if you remember from Newton's method that you've encountered in calculus, Newton's method is a method for solving nonlinear equations and optimization problems. And if you start close enough to the solution, it's extremely fast. It just zooms in to the solution very quickly, very accurately. But if you start far away, it may not even converge. That's what's happening here. There's a stability region within which the Newton step is effective, very effective, and another region far away where the method fails catastrophically because you are outside the region of convergence of Newton's method. So that's what I'm saying here. The convergence threshold, somewhere around here, is defined by the region of convergence of Newton's method. Now, this has far-reaching implications for both theory and practice. It suggests that if you are in the good region, then you don't need to worry at all. If you have a good neural network that starts you off in this area, you don't have to collect about being, to be concerned about being too accurate. You don't need to collect a lot of data. You don't need to use refined statistical analysis, confidence intervals, stuff like that. It's all irrelevant if you are in the good region. It doesn't matter. You don't going to get much appreciable, any appreciable improvement in performance. On the other hand, if you are in the bad region, and let's say your approximation architecture is poor, then no matter how much data you collect, no matter how smart you are in training the neural network, you're not going to, it's not going to help you. It's going to have marginal effect, and you're going to fail. So that's an important insight on which we're going to elaborate as we go along, and we're going to see it also in action. Okay, so let's go to linear quadratic problems, and we focus on a one-dimensional problem involving this linear system with A and B being scalars that are known, and a cost that's quadratic with positive coefficients Q and R. And the Bellman equation is given by this expression, and the optimal, and J star is a solution of this Bellman equation. And the main results here, which we talked about last time, is that J star is a quadratic function of X, with K star being the cost coefficient and being a solution of this Riccardi equation. Now, the Riccardi equation involves this Riccardi operator F. And it says that K star is a fixed point of this Riccardi operator. So we have to solve this Riccardi equation to find K star. Now, the optimal policy is also very conveniently characterized. It's linear of this form, with L star being the scalar coefficient of the linear policy, and it's given by this expression. So once you know K star, you can calculate the optimal policy. It's linear, and that's the coefficient. Moreover, you can find K star. Now, this is a nonlinear. Riccardi equation is nonlinear, so it's not solved by algebraically. Don't give it to MATLAB, does a matrix inversion. It's nonlinear. And it's a matrix equation in general. However, you can solve it iteratively by using value iteration, VI. Value iteration generates a sequence of optimal cost functions of finite horizon problems, K-stage problems. And as the horizon goes to infinity, you would expect that this JKs would converge to J star, the infinite horizon cost. And indeed, you can prove that this is so in this particular case. And these JKs are quadratic of this form, where KK is a scalar, which is obtained by iterating with the Riccardi operator K times, starting from a given initial condition, non-negative initial condition. And that's the form of value iteration. It doesn't iterate on the JKs, it iterates rather on the coefficients KK, and has this form. It iterates with the Riccardi operator that's given by this. So now we gave last time this graphical interpretation of the Riccardi equation and the value iteration. Okay, so here's K, and this red curve is the graph of the Riccardi operator. It's a nonlinear concave operator, and the optimal cost coefficient, K star, is obtained as the fixed point of this operator. Now, to find a fixed point, what we have to do is find the intersection of the graph, of the red graph, with a 45-degree line, and that is K star. So that's the graphical solution of the Riccardi equation. It gives us the optimal cost coefficient. And now let's go also to value iteration. remember, value iteration iterates with the Riccati operator. So at the typical iterate, kk, we calculate kk plus 1 by going up here. That's f of kk. Then we reflect this down to the horizontal axis. That's kk plus 1. And then we go and get kk plus 2 as f of kk plus 1. Then we reflect again, and we go on in this staircase manner to generate the sequence of iterates of value iteration. And you can see here that it converges no matter where you started, as long as you started within the positive axis. In fact, as long as you don't go, it works from anywhere up to this point here. It always goes from where, no matter what, it always goes to K star. This is a general property of linear quadratic problems. Here I'm talking about the one-dimensional linear quadratic problem. But there are multi-dimensional versions, which are very important in control theory, and all of this generalizes, except for the visualization. We have to consider one-dimensional problems, otherwise we would not have a visualization to look at, because K would be a matrix for the case of a multidimensional problem. Okay, so now let's go on with this visualization. Let's consider linear policies. In other words, policies of this form, with L being a scalar coefficient. How do you find the cost of those policies? Well, there's a Riccati equation associated for such policies. And it turns out that this Riccati equation is linear. Now, you would expect, of course, policies are just a special form. It's just having zero control, like the B coefficient being 0, right? And so you'd expect that there would be a Riccati equation corresponding to those in order that will give us this KL coefficient. And indeed, what's happening, it's a very simple derivation, very much along the line of the derivation for the Riccati equation corresponding to all policies. The cost of this linear policy is KL x squared. K is quadratic with KL being a scalar. That is the unique solution of the Riccati equation for linear policies. In other words, if you adapt the Riccati equation to apply just to linear policies, what you get is this with an operator FL that's specific to L, and it is of this form, and it is linear in K. Okay, this is the coefficient of K, and this is the constant. This is an equation in K, which can be solved in closed form to give you the KL coefficient. Now, this is true for policies such corresponding to this green line that slopes at an angle less than 45 degrees. Then you have an intersection with the 45-degree line. So if you have such a policy, which we call stable, with this coefficient here being less than 1, then this slope intersects the 45-degree line somewhere above K star. And this gives you the corresponding cost coefficient. But the policy doesn't have to be stable. If you choose a policy that's unstable in the sense that A plus BL is greater than 1, then you have a graph like this purple line here, which does not intersect the 45-degree line above the K star point. And here, for such unstable policies, the cost coefficient is infinity, okay? They have infinite cost, because unstable policies take the system off to infinity, and the state is penalized with a positive quadratic, and therefore the corresponding cost is infinite. So stable policies that slope at an angle less than 45 degrees, solving a linear equation gives us the corresponding cost coefficient. And there are also these unstable policies, which are lines that intersect somewhere in some irrelevant region over here. So now we have this red curve, the Riccati operator for the problem, and we have these lines which correspond to policies for the problem, linear policies. How are they connected? Of course, all these lines lie above the red line because these are suboptimal policies. They are not. They don't minimize anything. And what's happening, if you select the policy properly, you get those that are tangent to this red curve. So you can show in a simple calculation that you can find in your book that the graph, the red graph, is the lower envelope of the lines corresponding to the linear policies, stable and unstable. In other words, if you draw all these lines corresponding to all the possible policies and look at lines underneath, you get this red graph, okay? And now, it's also easy to see that as you draw these lines corresponding to, if you look at a particular K tilde, a particular cost approximation, then some lines are going to intersect above this point, but there's going to be some line that's going to be tangent to the red graph right at this point. And this is the line that we're interested in. This is the line corresponding to the one-step look-ahead policy. So the tangent line corresponding to a given cost approximation defines the one-step look-ahead policy with terminal cost K tilde of x squared. You can see that because when you apply one-step look-ahead, you minimize overall controls at the given state. So you look at all these points of interception with this, of the lines with this vertical, you look and you take the lowest one, and the lowest one is the one that corresponds to the tangent. It's an easy proof to see that. So we have these lines, and the one for a given K tilde, the one that corresponds to one step look ahead to this mu tilde is the one that's tangent at this point here. So this tangent linearizes the Riccati operator at K tilde. And linearization is a critical property for a Newton step interpretation. The way you interpret, you understand and you visualize Newton's method is that you linearize the given nonlinear equation around the current iterate and then solve the linearized problem to obtain the next iterate. So that's the figure I'm going to show you now. What I'm aiming at is to show that this step from here to here is a Newton step for solving the Bellman equation. So let's review together Newton's method for solving a generic fixed point problem, not the Riccati problem, but just some general operator G, one-dimensional, okay? So the way you learn it in calculus is that at a typical iteration, let's say Y here is the iterate. This Y star is the fixed point, of course, where we want to get. And there are these iterates, yk plus 1, and so on. And what we do at the current iterate is we linearize the G operator using a Taylor series expansion, right? This is the gradient of G at yk. This is the Taylor series expansion. And what we do, we replace G with its linearization, solve the linear equation, and that's our next iterate. In other words, the y that you get when you set this equal to y is the yk plus 1, the next iterate. So from yk, linearize, go up here, go down, yk plus 1, relinearize at the new point, and so on. And you can see that in this figure, the convergence is extremely fast. Of course, it's also possible that Newton's method does not work, diverges, because you start out at some point far from the solution, but it's a generic property of Newton's method that if you start close enough to the solution within its region of convergence, then you converge superlinearly, very fast. Now, this Newton's method is what you see in calculus books for one dimension, visualize it. But the theory of Newton's method, the superlinear convergence theory, extends very broadly to multidimensional problems, as well as problems where G is not differentiable. Is piecewise linear, for example. And this is an important point because in dynamic programming, the Bellman equation is not differentiable. It's very often non-differentiable. It's concave, typically, as it is here, and that helps the convergence. But then you have to worry about, if you're trying to analyze this figure theoretically, you have to worry about these non-differentiabilities. Now, all of this works out remarkably well, and you can find it in one of your textbooks, the Lessons from Alpha Zero textbook. But here we're going to stay with it. There are a lot of visualizations in that textbook, but here we're going to leave it at that. And we're going to return now to our approximation in value space figure. Okay. So this is the Newton step visualization, Riccardi operator, cost function approximation. This K tilde. At that point, we do the one-step look ahead minimization. That gives us this green line, and that gives us KL tilde. This is the coefficient of the one-step look ahead policy, and the corresponding cost coefficient is KL tilde. So the Newton step takes you from here to here. And superlinear convergence means that this thing here is much bigger than this thing. And as you approach, as K tilde approaches K star, the ratio between these two becomes very, very tiny and converges to zero in the limit. Okay, that's superlinear convergence. So if you're close, in one step, you get extremely close to the optimum. If you're far away, that's not necessarily true. And in fact, you may also go unstable. That's the key insight here. And all of this is very consistent with a lot of computation experiments, many computation experiments over decades now. Except that the Newton step interpretation is relatively recent. The experience, the computational experience, goes far decades. Okay, so here's a view of the one-step look ahead and the relation to Newton's method. We're looking at an online play picture with a cost function approximation that's obtained offline, right? Our standard conceptual framework. One-step look ahead, we consider all possible controls here and all possible next states, and each one of the next states is evaluated by this cost function approximation. And the Newton step is the one that maps this thing here into the performance of the one-step look ahead policy and has the superlinear convergence property. So now, let's consider multi-step look ahead. In particular, let's consider two-step look ahead in this figure. So instead, from here, we go to the quadratic cost approximations. We take one more step and then go to the quadratic cost approximation. Now, the important thing to remember about multi-step look ahead, in particular L-step look ahead on K tilde, is that it is a one-step look ahead on K tilde after it has been iterated with a Riccardi operator L-1 times, right? So the previous figure was one step look ahead, and instead of having this in multi-step look ahead, what we have is this entire thing that includes an extra step, or more generally, N-1 extra steps with a Riccardi operator. So L step look ahead is really one step look ahead. It's just is applied to a bigger thing that includes these value iterations which enhance the starting point of the Newton step. And only the first step of the lookahead is a Newton step. The other stuff helps to bring the starting point closer to where you want to be. So let me give you another view of this. Here we are with the Riccati operator, the graph, the Riccati operator, and we consider K a cost function approximation, K tilde, and let's look at the two-step look-ahead policy. What we do is we apply a value iteration step to K tilde, which brings us here to K1, and then we apply the Newton step to obtain this KL tilde. So this is the value iteration and corresponding to the second step of look ahead, and this is the Newton step corresponding to the first step of look ahead. So this is for two-step look ahead. If I had 10-step look ahead, then this picture would be 9 of these little value iterations and then a Newton step. And these 9 iterations help you to enhance the starting point for the Newton step, bring it closer to K star, and therefore have a better chance for convergence, superlinear convergence. So that's the key insight. It's the first step of the look ahead that is the Newton step. And this now brings another insight into play, namely that the first step is the one that's important. The rest is kind of subsidiary. They could be approximate, but the first step has to be exact as you can. So in L-step look-ahead, model predictive control or approximation in value space, only the first step of look-ahead acts as a Newton step. The remaining L-1 step only serve to enhance the starting point of the first Newton step. And the important insight is that the first minimization step should be done exactly. Otherwise, the Newton step will be degraded. And that's the key point, the key thing in the XR architecture. The remaining steps can be done approximately. And this is a very important insight in a number of settings. In particular, let's suppose that you have a stochastic problem, not a linear quadratic problem, but a stochastic problem. Each step of look ahead in stochastic problems costs a lot because the look ahead tree increases much faster in stochastic problems due to the fact that you have to take into account the stochastic disturbance. Now, the look ahead tree would be simplified a lot if you were to replace it with a thinner tree involving deterministic transitions. So, and how do you do that? Well, you can use some kind of a certainty equivalence approximation in all the look-ahead steps except the first. The first should be stochastic and accurate. The subsequent steps, they can be deterministic approximations using some form of certainty equivalence assumption, scheme like that, or perhaps some other thing. We're going to play with things like that in the course later. But this idea has been verified over many years, starting with this paper 25 years ago, on many settings. It's the first step that's important, not the remaining steps.
All right, let's get to the lecture. We're going to start talking about the region stability and rollout and policy iteration. As mentioned earlier, the stability is an important issue in control theory. And intuitively, what stability means is, for example, if we want to control the room temperature, we want the temperature to stay some constant value, the value that you set to be desirable to your feeling, rather than fluctuate dramatically, right? So instability would mean this temperature fluctuate dramatically. Then the question arises is, if we apply approximation in value space, how can we ensure the resulting control is stable? For example, if in the context of linear quadratic problem, a stable policy means its cost function has finite value, which again translate to the cost coefficient means the cost coefficient has finite value. So starting from some k tilde, as mentioned in the first part of the lecture, one-step look ahead will define a policy by drawing this line that is tangent to the point k tilde, and its corresponding cost function will be the intersecting point between the 45-degree line and the newly drawn tangent line. So if we look at this point, and suppose this is our cost function approximation coefficient, we do one-step look ahead, and this is the point of the resulting one-step look ahead policy, and it's stable. On the other hand, if we look at this point, suppose this is our cost coefficient, and we do one-step look ahead, we get a line, we draw a tangent line whose slope is larger than 1, as shown here. As a result, it does not have an intersecting point with 45-degree line among the positive part. It has an intersecting point below 0, but that is not the that does not correspond to its cost function. It has no relation to its cost function. In fact, its cost function is infinity everywhere except 0. So then the question emerges is that from where we should choose those k tilde, and all those k tilde that leads to a stable one-step look ahead policy, we call it the region of stability. So the region of stability composed of k tildes such that its one-step look ahead policy is stable. So in addition, if we use two-steps look ahead policy, then it will have a different region of stability. The reason is value iteration brings k tilde close to k star. Suppose, let's say, at the same k tilde, instead of one-step look ahead, we do two steps look ahead. So, which means starting from here, we're gonna first do one value iteration step. That leads us to here. And then from this point on, we do the Newton step. And in this case, the resulting two steps look ahead policy is stable. Therefore, with different number of look ahead steps, the region of stability are different, and the region of stability expands as the look ahead steps expand. So increases. So this is one of the reasons that we want to use as long look ahead steps as possible. And in fact, we can provide exact description and calculate exactly where or how the region of stability looks like for this linear quadratic problem. Again, if we see we draw the Riccati operator for some unstable policy, we're gonna have a line with slope larger than 1. And on the other hand, for any other stable policy, we will have a line with slope smaller than 1. And the region of stability, in fact, is a ray starting from this point onwards. So starting from this point, case S, moving to the right, are all the points on this ray belongs to the region of stability. The reason is, as you can see on this figure, if we pick some point here and draw the tangent line, its slope gonna be smaller than 1. And therefore, the start of the Newton step must be within this region of stability in order to have a stable policy. And another character that you notice here is that if we choose K tilde to be somewhere here in this region from Ks to K star, you draw the tangent line, and here the curvature is still a little bit larger in comparison with this part. This part is rather flat. And a benefit of that is, suppose, let's just imagine that from this point on, if the curve become entirely horizontal, then what's going to happen? You choose any point from this side on, and you do one step look ahead, you get optimal policy, right? Because if this part is flat, then immediately you draw the tangent line, you get this point. So on the other hand, here is not entirely flat. It's not entirely horizontal, but it's rather flat, which means you draw a tangent line, you get something which is still very close. And the good news is all the cost function of stable policies, their values fall into this part, which is natural because K star is the coefficients of optimal cost function. So any policy, its cost function must be larger than K star. The coefficients must be larger than K star. So it's on the right-hand side of K star. Okay, that brings us to this visualization, the visualization of rollout with stable linear base policy. So recall that in rollout, what we do is we use a cost function of the base policy as J tilde. And then based on this, we do one step look ahead. So suppose that this is the Riccati operator of a base policy, mu. What we do is we first calculate the cost function of mu by inspecting the intersecting point of its Riccati operator and the 45-degree line. We get this point, right? And this is the cost function, cost coefficient of base policy mu. And then starting from here, we do Newton step by drawing this tangent line. You can see this part is rather flat. And after drawing tangent line and find the cost function of mu tilde, it's much closer to J star compared with the distance of the initial base policy. And the good news, another good news is rollout preserves stability. So if the starting base policy is stable, then it's always true that the lookahead policy we obtain is also stable. In this context, we call it rollout policy, right? So this is the base policy and this is the rollout policy. So starting with the base policy, if base policy is stable, then rollout policy is also stable. And as we emphasized many times, rollout is very reliable. In practice, it's very consistently outperform a lot of complicated methods. And another good thing is it's very easy to implement. So we're going to show that in some examples in later lectures. Given that rollout is one Newton step, and policy iteration, in fact, is repeated rollout, whereby each iteration of policy iteration is one Newton step. So it's full-fledged Newton step applied to solve the Bellman's equation, or in the linear quadratic problem, Riccati equation. So starts with a linear policy mu0 equal to L0x. It generates a sequence of linear policies with two-step process. It starts by perform policy evaluation, which is calculate the cost function of mu k, where mu k equal to Lk times x. So you calculate this infinite long trajectory and find out what is the cost function of it. As it turns out, suppose that L is stable, right? Start from L0 that is stable. And it turns out there's a explicit formula for this cost function, which is looks like this. And that requires A plus BLK to be smaller than 1, right? If A plus BLK is bigger than 1, then we don't have a finite cost. So after you calculate this, you perform policy improvement step, and we went through the detailed calculation in the previous lecture, and essentially it's for every x you do set the derivative with respect to u to 0, and you can get this formula. So 1 Newton step means starting from kk, that corresponds to a policy mu k, you get k plus 1, which corresponds to the cost function, which is the cost function of the improved policy. So that's the Newton step. So starting from some kk, you get a k plus 1, where k plus 1 is the cost function of the improved policy. So starting from a cost function, you get a new cost function, and the distance between those is the ground covered by Newton step. As a result, rollout is a single Newton iteration, and policy iteration is full-fledged Newton's method for solving the Riccati equation. Again, starting from the cost function of some policy, and you get a cost function of the improved policy. Important variant, optimistic policy iteration, consists of repeated truncated rollout iteration. So basically, what I mean here is in policy iteration, given a policy mu k, we calculate exactly its cost function by this formula. But in some context, other than linear quadratic problem, for example, if there are additional constraints on x, then you cannot calculate exactly the cost function of a given policy. The best you can do probably is just run simulation under that policy for a few steps, let's say m steps, and then plug in some terminal cost approximation. Use this to approximate the cost function of a given policy. And the corresponding method will be called optimistic policy iteration. So using a finite trajectory cost plus some terminal cost approximation to approximate the cost in case that you cannot solve the cost exactly, and then do the policy improvement and repeat this procedure. And mathematically, this can be viewed as Newton SOR method, repeatedly apply a Newton step preceded by first order value iterations. So SOR here stands for successive over relaxation, and VI here, of course, stands for value iteration, but it's not value iteration involving minimization. It's value iteration corresponds to a given policy. So this FL operator, not F operator. All the points that we have discussed thus far admits generalizations. The Newton step interpretation of approximation in value space generalized very broadly to stochastic problems, to Markovian decision problems, to risk-sensitive problem, and you name it. A lot of generalizations, and some of the mathematics can be challenging, but in this textbook, lessons from AlphaZero, it mostly focus. Okay. All right. So For those generalizations, in the generalizations, the Riccati operators are replaced by Bellman operators. And the Newton's method for solving the minimizing Riccati equation become Newton's method for solving the minimizing Bellman's equations. Recall that Bellman's equations are one equation for a state. So if we have 10 state, we have 10 equations. If we have infinite state, it becomes infinitely many equations. It's a functional equation. And in a lot of dynamic programming problems, you will see that the corresponding Bellman's equation is not differentiable. So the Riccati equation, the curve, you can see it's a smooth curve, right? But in a lot of dynamic programming problem, for example, Markovian decision problem, you can see later, or you read about in the reinforcement learning literature, it's piecewise linear, which means there are some edge point connecting the piecewise linear stuff. So it's not differentiable. On the other hand, non-differentiability is not an issue. And there is a proof in the appendix of the textbook for you to consult to show that this superlinear convergence still hold. And approximation in value space is still a single Newton iteration enhanced by multi-step lookahead and by truncated rollout if those two are involved in your design formulation. Rollout is a single Newton iteration starting from the cost function of the stable base policy. And exact policy iteration is a full-fledged Newton's method. And multi-step lookahead and truncated rollout enhance the stability properties of the policy produced by approximation in value space. Okay. Any questions? Now let's get to the next session. The art of formulating practical problems as dynamic programming. As we have mentioned earlier, that dynamic programming is a very powerful modeling tool that allows the principle of optimality holds regardless of nature of state and control and so on. So a lot of problems can be formulated as dynamic programming problems. On the other hand, it is sort of an art to know, given a practical problem at hand, it's sort of art to know what is the state, what is the control, and how do I design the stages and so on. Fortunately, there are some rule of thumb, and we provide an informal recipe. Typically, it will be clear, given a practical problem, that what is the control in this problem. For example, if you have an investment problem, then of course the control is how much money you have and you put on in market, right? And if you have a problem of control a vehicle, then the control is whatever you control, the steering wheel, the gas pedal, and so on. So typically, it's a good idea to first define controls and then the stages. The stages can be defined when the information are available. Essentially, those informations are used for us to make decisions, to select controls. Therefore, you should consider it's a new stage if new information emerge that helps you to make the decision. And based on those two, you can design what is the state in the problem. And unlike control, which typically will suggest itself, states in a given problem, there can be many alternatives of states. But typically, we define as state something that summarizes the past for the purposes of future optimization. Essentially, that means as long as we know xk, all the past information is irrelevant. Suppose that you okay. So in mathematical literature, this is typically called Markovian character, right? Or Markovian property. Essentially, all the past information can be forgot once you have this information. This piece of information is available, and the rationale is the controller applies action that depends on the state. So the state must subsume all information that is useful for decision and control. As I alluded to earlier, there are a lot of different choices of states given the same problem. In the traveling salesman problem, we need to include all the relevant information in the state. For example, the past city visited and the current city. Other information such as the costs incurred so far need not be included in the state. The reason is how much cost has incurred in the current past does not help us to decide which city to visit next. In the examples that we're gonna talk about in later lecture, actually we're gonna provide an application of such problem. It's called partial or imperfect information problems, whereby we use noisy measurements for control of some quantity of interest yk that evolve over time, which we don't have precise access to. So the best we can do is we measure it with some noise involved in the measurement. And the best we can do is just collect all the information, or one way we can deal with this situation is to use the collection of all the measurement up to the current stage as state. And this is typically denoted as IK and referred to as information state. On the other hand, it may, for this partial or imperfect state information problem, it may also be correct to use alternative states. For example, the conditional probability distribution. For example, if based on the measurement, the entire historical measurement, we have an inferred probability of at the current stage k, what the real state yk is. So this is a probability distribution over, conditional probability distribution over the quantity of interest. Then this can also be used as state. And this is called belief state and subsumes all the information that is useful for the purpose of control choice. So those are the alternatives of state choice. All right. We have discussed thus far problem formulations where the next state, xk plus 1, depends on xk, uk, and wk. What if there are delays involved in the problem, by which I mean the next state not only depends on the current state, but also depends on the previous state. And the control not only depends on the current state, but also previous state. Then this formulation, this system equation does not fall into our standard framework, but a generic technique that we can use is called state augmentation. Essentially introduce additional state variable, yk and sk, and to define a augmented state with higher dimension, whereby we define yk, a new state, and sk, such that they record the values of xk plus minus 1 and uk minus 1 that still the next state depends on. As a result, we have this new state, xk, k plus 1, y, and s, and its corresponding new system dynamics in this form, and define xk tilde as augmented state, as the new state, and we have a new system equation where this fk tilde is this whole thing, and yxk tilde is the augmented state. And now this new system equation looks a lot like our standard formulation, right? And then we can, for the reformulated problem, we can use the dynamic programming algorithm starting from the terminal state and operate on the augmented states. So here this thing gonna become fk tilde with xk tilde, uk, and wk, right? This kind of state augmentation not only appears in delay, this sort of situation, but also in many other situations. For example, if there are some restrictions on not only the current control, but also the preceding control. For example, you want to select control that not only depend on xk, but you also want control that uk that does not change so much with the previous control. So what you do is you record the previous control and treat it as a part of the augmented state and impose constraint on this augmented state. Another situation is, for example, in forecasting, if you have a store to run and all of a sudden you get the forecast that the demand of your product gonna increase threefold. And that's obviously helps you to make decision at the current stage. And this kind of information can be incorporated in the by state augmentation technique. The state augmentation technique is very useful. However, it has this problem that suppose that we augment a lot of stuff in our augmented state, then originally this xk may be a low dimension. Now after state augmentation, it becomes high dimension. And high dimension is always a problem for dynamic programming algorithm. So all of a sudden, the previous problem may have low dimension, looks feasible, and after you do augmentation, in principle, dynamic programming algorithm works, but not in practice anymore. Fortunately, the state augmentation stuff does not affect the approximation in value space method we discussed, because in approximation in value space method, we only operate on the current state in the online operation, right? In the online play operation, we only look at the current state and do the minimization. So the state augmentation technique does not impact negatively computationally for the approximation in value space method. So another type of problem are the ones with a cost-free and absorbing terminal state or goal state. And typically we can view them as infinite horizon problems. The reason is we don't know beforehand how many stages going to be involved in this decision-making process. We know there's going to be a termination at some point, but we don't know when. On the other hand, it may be possible to convert to a finite horizon problem, introduce as horizon an upper bound to the optimal number of stages, assuming such a bound is known. Let me use the shortest path example again. Suppose I want to travel from here to Boston and drive from here to Boston and want to find the shortest path. Then I don't know beforehand how many cities I'm going to drive through, but I do know the number of American cities. So the worst case is the worst stage number can be the number of cities in United States, right? So that's a bound. Another bound is if you if you are a bit more knowledgeable than me, you may have a good guess. Okay, I'm gonna drive through 30 cities, probably. So you can use that as an upper bound of the problem. And then add big penalty for not terminating before the end of the horizon. So let's look at an example. A multi-vehicle moves simultaneously one step at a time in order to finish the tasks. So suppose we have vehicle 1 and vehicle 2 in this road network, and they are in collaboration in order to get to those 2 nodes to finish the job as quickly as possible, to minimize the number of moves, to perform all tasks to reach the terminal state. So in this problem, what you will define as states, as control, and terminal state and horizon. Start with states. What do you think can be a good candidate for state in this problem? Sorry? The nodes in the ground.
Vertex in the ground.
Sorry?
Visited so far, so like for vehicle at a certain location, the state would include whatever we have visited so far.
Yeah, that's a possibility. So it will be all the nodes visited by vehicle 1 and all the nodes visited by vehicle 2, right? So that's a possibility. Sorry? Yeah, that's a possibility, but it missed something. So for example, suppose that vehicle 1 and vehicle 2 are at the current position, like what is shown in this figure, compared with vehicle 1 and vehicle 2 at the current position, but node 7, there is no dollar left anymore. Of course, that would be different, right? So, of course, this gentleman mentioned that the current entire trajectory of vehicle 1 and vehicle 2, that's one valid option, but it's not the most efficient option. The most efficient option would be the current location of vehicle 1 and vehicle 2 and the remaining task, right? So you can have 2 parts of the state. One is the position of vehicle 1 and vehicle 2, and the other part is the remaining task. So that would be the most concise state that includes all the information that is needed for our control selection purpose. So what is control in this problem? Yes, so it must be the product of, so all the ordered pairs of vehicle 1 and vehicle 2 can move next, given the current position. And the terminal state gonna be the state where there's no dollar left in the graph, right? So using my previous formulation of the state, it will be that whatever the current state of whatever the current position the vehicle 1 and vehicle 2 is, and there is no task remain. And that's all those states lumped together will become the terminal state. How about horizon? So if I want to formulate this problem as a finite horizon problem, what are the good suggestions for horizon? Sorry? That will work if there is only one if there will be, why all position combined will work? Yeah, kind of, because for example, if let's say I decide vehicle 1 gonna go for the task at node 9, and vehicle 2 gonna go for the task at node 7, then the longest distance that vehicle 1 need is the number of node, and vehicle 2 need is number of node. Since they operate simultaneously, then the number of node can be a valid option for horizon, right? So that's one option. But if you have better guess, then it's better to use more accurate guess. This problem all looks simple and easy, but when you increase the number of vehicles, the problem can be very difficult to solve. And one of the primary challenge is that, for example, if we do one-step look ahead, we need to enumerate all the controls available at the current stage, right? In order to make the decision what option we choose next. Here we have 2 vehicles. So in total, in this case, we have 4 options. Suppose that we have 10 vehicles, and at each stage, each vehicle have 2 options to choose. Then our minimization would need to calculate 2 to the power 10 numbers. And this thing can grow quite quickly. Suppose there are 20, then it's 2 to the power 20, 2 to the power 50. Quite quickly, this problem become not manageable to use standard one-step look ahead method. So, and this is a good candidate for multi-agent framework we're going to introduce next. Multi-agent framework has a long history, dates back to the 60s. And the defining character of multi-agent problem is that there are multiple agents collecting and sharing information selectively with each other and with an environment, or you can think it as a computing cloud. So if you look at here, there are agent 1, 2, 3, 4, 5, and they collect the information and they share information with each other selectively. And in this figure, some agent has access and can receive information from the environment or the computing cloud where others cannot. And agent I applies decision UI sequentially in discrete time based on the information it received. So at each stage, the entire control is composed of M component, each one associated with one agent. There are 2 types of multi-agent problems, which are completely different in terms of difficulty and in terms of whether or not can be treated by dynamic programming. The first type is called the classical information pattern, where agents are fully cooperative, fully sharing, and never forgetting information. And this problem can be treated by the standard dynamic programming. So in that case, all the information that is available to agent 1 is also available to all the other agents. And they are cooperative. They are fighting for the same goal in order to minimize the same cost. And this problem can be treated by dynamic programming. Whereas the non-classical information pattern is where agents are partially sharing information and can be antagonistic. So as shown in this figure, agent 1 clearly has access to information that is, suppose that here all the information available to agent 1 is not shared through this line, then agent 1 has more information, and maybe their cost function are different. For example, if they are working for a different company, then they have their different agenda. They will not, if they don't collaborate and so on, then this problem will not be treated by, cannot be treated by dynamic programming therefore it's quite hard. Because for agent 1, it has a cost function G, whereas for agent 2, it has a different cost function, and each minimize its own cost function, and it cannot be treated by dynamic programming anymore. But we will focus here on the classical information pattern case, where at each time, agents have exact state information and choose their control as a function of state. So this exact state information, which is shared by all the agents, therefore, the picture looks like this. Every agent has the same access to the sensory information stored in the information cloud, and every agent get its control decision computed by the computing cloud that collected all the available information. The model we use is discrete time, possibly stochastic system with state X and control U. So the state X is all the sensory information collected by individual agents and shared with the computing cloud. And this is available for control selection of not one, but every control element used for different agent. Note that the agent here is just a metaphor. The important thing is this mathematical structure that the collective control is composed of different components that we need to select simultaneously. For example, each agent can be located physically in different location. For example, it can be individual robot, and when they collaborate and cooperate in a warehouse situation, so each one of them can be located differently and choose their control selection, do the control selection. But it can also be that each agent, all the calculation is done by the same computer and located at the same place. It's just we view the control selection purpose of individual component as done by different agent. The theoretical framework for this problem is dynamic programming, and we will reformulate for faster computation. We'll first aim to deal with the exponential size of the search and control space. Later, we will discuss how to compute agent control in distributed fashion. In the process, we will deal with, in part, the non-classical information pattern issue. Now, let's look at a very interesting small example, which is the spider and fly example. And this is, despite being very simple, it can be used in a variety of contexts, including vehicle routing, maintenance, search and rescue, and firefighting examples. And in the previous offering of this course, some students in their research project has used this kind of applied what they learned in this kind of application. And for those of you who are interested in coding and so on, problem of similar type can be a good practice and can be a candidate for your research project to try out some of the the material covered in the course. So in this example, we have 15 spiders move in 4 directions with perfect vision, and 3 blind flies move randomly. By randomly, we mean that it has a given distribution. Basically, if it's here, then the next instance, it goes to here, 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 or here is equal probability, let's say, or whatever probability that you have defined. The objective is to catch the flies in minimum time. Now, if we use one-step lookahead, we have this minimization given the current time. We have this minimization that we minimize among all the available controls, right? And find what is the best one. Now, in this problem, note that we need to select moves for 15 spiders simultaneously, and each one of them maximum can have 5 choices up and down, left and right, stay still. So in total, roughly, there can be 5 to the power 15 joint move to choose, which means we need to calculate this amount of numbers and compare them and find the minimum in order to decide the moves for 15 spiders simultaneously, which can be quite daunting and infeasible in real time because we need to do this calculation in real time. We will reduce to 5 times 15, which is 75 number comparison in our reformulation, while maintaining the good property. The key idea is to break down the control into a sequence of one-step spider at a time moves. And there are a lot more materials of this application, and with animation, you can find it here. Now, this reformulation idea is to trading off control and state complexity. Basically, by reformulating the problem such that we consider a control and a state and partial control as a new state. And this idea dating back to the neurodynamic programming book in 1996. And there is an equivalent reformulation by unfolding the control action. So given that we're currently at state X, the previous formulation is that given X, apply control, we get to X bar, a new state where a random cost G of X, U, and W incur, and transition occurred in this form. By contrast, this reformulation consider also as a state or as the control of X is the first component of control, U1. Therefore, you get to a new state, X and U1. And at this point, you apply control U2, and you get to a new state, which is X, U1, and U2, and so on. Until at this point, X, U1 until UM minus 1, you apply the final control component corresponds to the last agent, and you get to the new state. So the control space is simplified because at each state, there's only one control component to choose at the expense of M-1 additional layers of states and corresponding M-1 cost functions. This allows far more efficient rollout calculation because, as you may recall, that here in this stage, if we apply rollout, we just choose all the feasible U1 and move on to the next stage and so on. But the question is, how will we decide U1? How do we deal with U2 and so on when we are computing U1? How do we deal with all the subsequent ones? That's will be clear shortly. So this allows far more efficient rollout, and it's just standard rollout for the reformulated problem. So it is a Newton step applied to solve this reformulated problem. Note that this reformulation makes little sense if we want to apply dynamic programming to solve it, because suppose here is a scalar state. After we do reformulation, now the problem state space become M plus 1 dimension. So from the original scalar problem, we have a high dimension dynamic programming problem. So it makes little sense when we apply dynamic programming. However, it makes a lot of sense in the context of rollout. The increase in size of state space does not adversely affect rollout. Only one state and its successors are looked at each stage during online play. And the complexity reduction is dramatic. The one-step lookahead branching factor is reduced from n to the power m to n times m, where n is the number of possible choice for each control component UI. We'll discuss special types of problem domains and reformulations, including POM-DP, adaptive and model predictive control in the next lecture. In your homework 3, which due in 1 week, is exercise 1.2 of the latest version of the class book. And you are encouraged to read ahead section 1.6 of the latest version of the class textbook. And a good time to watch a summary video, as well as the other textbook that covers a lot of theoretical ground. All right. Thank you for your time.